Welcome to the lesson on the measure phase of Six Sigma DMA-IC model. Upon completion of this lesson, learners will be able to explain the measure phase of the DMA-IC model and recognize the tools associated with the measure phase. Now that the Six Sigma team has a good understanding of the current production process and the customer requirements, they can begin the measurement phase. A key component of the Six Sigma model is strategic data collection. Data is very important to understand both the current system and also to determine if any improvements were made after the completion of the process. In the measure phase, the team translates the goals of the project contract into a structured measurement plan, performs the measurements according to that plan, and formats or stores the data for further analysis. The measure step tells how well the current process is meeting the customer requirements and shows the potential of the process for meeting these requirements in the future. The measure step also provides the team with strengths and weaknesses in the process. Careful measurement planning is critical due to the time, resources, and financial costs involved. The measurement plan outlines what to measure, measurement types, data collection methods, and storage procedures, sometimes including target specifications and sampling details. Project goals and critical to quality requirements from the defined step guide the team in determining what needs measurement. Defining measurement types is essential, typically focusing on three areas: input measures for job completion, process measures, and output measures important to customers. Teams are advised to collect data from input, process, and output sources, although historical data may sometimes suffice. The main goal of the measurement planning step is to provide a measurement method so that the best and most accurate data on the process performance can be collected. This allows the team to compare the performance of the current system to the target specifications for the future system. Data can be categorized into two main types: discrete and continuous. Discrete data includes binary information, such as yes, no, or true, false responses, and countable whole units like the number of defects or customer complaints. This type of data is often represented as percentages or ratios, such as defect rates or yield. On the other hand, continuous data is measurable on a continuous scale and includes variables like time, weight, length, or temperature. Unlike discrete data, continuous data can take any value within a range, including fractions or decimals, providing a more nuanced representation of measurements. Because measuring the entire population of data is usually impractical, determining sampling techniques is also an important step in the measurement plan. Sampling means measuring only a small proportion of the overall available data. The sample population selected must reflect data that is random, independent, and representative of the entire population. Now that the measurement plan is complete, the actual measurements can be taken. A few commonly used measurement tools are check sheets, the calculation of baseline sigma, and the process capability measurements. A check sheet is a data recording and compilation tool that can be structured as a table, worksheet, or form. Check sheets can record information like the frequency, time, or location of an event. Examples of events include the breakdown of machinery, process defects, or non-value-added steps in the process. An example of a check sheet is shown here. Calculating the baseline sigma provides the starting point of the process performance by calculating the current number of defective parts produced per million. The easiest way to calculate the baseline sigma is by identifying the unit of interest, which is typically the final product received by customers, defining the defects, and determining the number of opportunities for each defect. Defective parts per million opportunities, abbreviated as DPMO, is calculated by dividing the number of defects by the number of units times the number of opportunities, all multiplied by 1 million. From this, you can use a conversion table to determine the baseline sigma level of the production process. Let us look at an example. Let's assume that an electric vehicle motor manufacturer is calculating their baseline sigma. The unit of interest in this situation is the individual motor units produced. The product is considered defective if the motor insulation is inadequate, the rotor bearings are misaligned, or if the motors have incorrect winding configurations. Therefore, the number of defect opportunities is 3, one for each problem. Let's say the project team studies 100 motors and finds that 2 have inadequate insulation, 4 have misaligned rotor bearings, and 1 of them have incorrect winding configurations. First, let us calculate the defects per million using the standard equation. It turns out to be 23,333. Then, using the conversion table that we discussed earlier, we find that this value corresponds to a baseline sigma value between 3.4 and 3.5. Achieving performance at the Six Sigma level means that there would be only 3 defective parts per million produced. The process capability is another statistical baseline measurement that reflects the potential capability of a process to meet certain performance goals. Process capability is determined by a capability index, known as CPK. The capability index is calculated using the process variation, the mean, and the specifications set by the customer. In other words, process capability is used to determine whether a given process is capable of producing a product that meets customer satisfaction. In summary, the measure phase of the DMAIC model requires a detailed and structured data collection plan to further understand the current process. There are 2 types of data that can be collected during the measure phase: discrete data and continuous data. Tools used in the measure phase include check sheets, baseline sigma, and process capability. Once the data is collected according to the measurement plan, the collected data should be stored or represented in such a way that analysis can then take place. Thank you.